We begin chapter 12 discussing the formation of radicals and then looking at some simple reactions of them. So, if you remember, there are really only two ways of breaking a bond. Now, the first one was emphasized in the first semester, and that is called heterolytic cleavage. So, we can look at a very simple example here of ethane. And if we were to heterolytically cleave ethane, what that means is that the two electrons from that bond go to one of the atoms, and the other atom doesn't get any of them. And of course, we denote that using curved arrow notation with the double barbed arrow, right? So here I'm showing that the two electrons from that carbon-carbon bond are moving toward the carbon on the right. The result is the carbon on the left now becomes a carbocation, and the carbon on the right, the one that has accepted those electrons, becomes an anion. And so these are ionic compounds, and hence we looked at substitution elimination reactions like with these types of scenarios in terms of heterolytic cleavage. Now, conversely, homolytic cleavage involves the breaking of a bond where one electron of that bond goes to one atom, and the other electron goes to the other atom. And so again, we can look at ethane as our example. And so we show that movement of electrons using the fishhook arrow. So I'm going to take that carbon-carbon bond, and I draw a fishhook arrow from the bond to the carbon on the left, and then I'm going to take another fishhook arrow from the bond to the carbon on the right. The result is that both carbons receive one electron, and it is not paired up, so we call this a radical, right? And so we end up here, in this case, with two methyl radicals. Now it happens that homolytic cleavage requires less energy than heterolytic cleavage. So you never see ethane undergoing a heterolytic cleavage. You never see the formation of methyl carbocations and methyl carbanions. If ethane were to break, one electron goes to one carbon, the other electron goes to the other carbon. And we call this the bond dissociation energy. Now, even though it requires less energy than heterolytic cleavage, it still requires a lot of energy, namely 376 kilojoules per mole to break that carbon-carbon bond in ethane. And so in order to break that bond, you need harsh conditions, either a lot of energy in terms of light or a lot of heat. So nevertheless, we can look at very simple alkanes and we can heat them up, and they will undergo this bond breakage. And that process is called pyrolysis. And this is often done, we'll see, in terms of oil refinery. So let's take a look at ethane again. And of course, we just looked at how ethane undergoes a homolytic bond cleavage. Right? So I'm going to draw that up again. And with heat, I get homolytic cleavage. So I draw one arrow going to the carbon on the left, the other arrow going to the carbon on the right. Again, the two fishhook arrows. I'm trying to emphasize this to you so that you get used to the idea of drawing fishhook arrows instead of the double barbed arrows. And of course, we see that you get these two radicals, and those two radicals are called methyl radicals, right? Now, if we go to a little bit more complicated alkane, we can take a look at propane, right? So propane, C3H7, the Lewis structure looks like this, or the condensed formula looks like this, and propane has two carbon-carbon bonds. Both of them can be homolytically cleaved, and the result is going to be the same, right? So that regardless of whether I homolytically cleave the bond on the left or the right, I get the same species that result from this. So when I heat this up, I end up getting these two radicals. And the radical on the left, you should kind of know what the name of it is, but it is called an ethyl radical. And of course, we see another methyl radical being formed. So when propane undergoes pyrolysis, it forms ethyl radicals and methyl radicals. And I can go a step further and look at butane. And the condensed formula for butane looks like this. And so when I heat butane up, now butane has 3 bonds. And so I can get different products depending on what carbon-carbon bond undergoes cleavage. So if I take a look at the carbon-carbon bond furthest on my left, right, at the terminal end, I can draw that homolytic cleavage, right? So again, a fishhook arrow going to the carbon at the end, and then another fishhook arrow going to the carbon to the right of it. And the result is that I get these two radicals. And of course, the radical on the left is a methyl radical, and the radical on the right is a propyl radical. Now, this is only one way of that butane can undergo homolytic cleavage. I can show another way where I'm taking that central carbon-carbon bond and undergoing homolytic cleavage. So again, my 2 fishhook arrows denoting one electron going to the carbon on the left and the other electron going to the carbon on the right. And the radicals that are produced look like this. And of course, they're 2 of the same type of radical, namely the ethyl radical. And we can think about larger alkanes, and of course, the larger the alkane is, the more types of radicals it can produce. Now understand that in pyrolysis, when these radicals form, they are very reactive. And they can react in 4 different distinct ways, and we're going to look at each of those 4 distinct ways. The first one is what we call hydrogen abstraction. So what happens is, and if we were pyrolyzing butane, remember in the pyrolysis of butane, you can get methyl radicals, ethyl radicals, and propyl radicals. And any one of these radicals can react with butane itself. And so here I'm just denoting a generic radical. So keep in mind that that radical can be a methyl, an ethyl, or a propyl group. Now, this radical, so hydrogen abstraction as the name implies, the radical is going to remove a hydrogen from the alkane. And of course, butane has 2 different types of hydrogens, right? It has primary hydrogens and secondary hydrogens. And so we can see that if a radical abstracts a primary hydrogen, and we denote that by showing the electron from that radical that's combining with an electron from a carbon-hydrogen bond, right? So we're forming a new carbon-hydrogen bond, and of course so that bond between carbon and hydrogen of butane still has 2 electrons, so that second electron goes to the carbon. The result is that I generate a butyl radical. So I'm showing a red dot here as that radical to kind of highlight that radical. And of course, in the process, I get RH. So I'm generating an alkane again. So notice if I used a methyl radical as my radical, I would generate methane. If I used an ethyl radical, I would generate ethane. And if I used a propyl radical, I would be generating propane. Now, as I said, butane has two different types of hydrogens, the secondary hydrogens and primary hydrogens. So I can show that a radical can abstract a secondary hydrogen as well. And again, the process is the same as above, where I'm taking that one electron and I'm combining it with hydrogen, so I'm creating a carbon-hydrogen bond, and the remaining hydrogen goes onto the carbon of butane. And so the result is, this is called a sec-butyl radical. So in the first one I get a butyl radical, and in the second hydrogen abstraction I get a sec-butyl radical. And then I get an alkane that's produced. And so you see when hydrogens are abstracted, we get alkanes, right? And the alkane could be methane, ethane, or propane. And then you're generating more radicals. So this is one way of producing smaller alkanes from larger alkanes, right? So I start with butane. Butane undergoes pyrolysis to form radicals. Radicals can abstract a hydrogen from butane, and those radicals then are smaller alkanes. The second type of reactions that radicals can undergo is called disproportionation. So this is when a radical can remove a beta hydrogen from another radical. So we're talking about two radicals reacting with one another. Again, we know that butane forms methyl, ethyl, and propyl radicals, and so if we're focusing on the pyrolysis of butane, we can think about how these radicals can actually react with themselves. And so I'm going to show as my example the ethyl radical. So this is the ethyl radical, and I've highlighted on the beta carbon. So we're talking the carbon that's adjacent to the radical. If the radical carbon was the alpha carbon, then any adjacent carbon would be the beta carbon. And I've highlighted that carbon-hydrogen bond to it. And so what happens is another radical, be it a methyl, an ethyl, or a propyl radical, can abstract a beta hydrogen from this ethyl radical. And so we show it very similar to the way we show hydrogen abstraction, right? Because we're essentially abstracting a hydrogen. But in this case, once you form that carbon, the new carbon-hydrogen bond, the electron that's left over doesn't form a radical, but instead it goes to form another carbon, a carbon-carbon pi bond with the radical on the alpha carbon. And so the result is ethene. So I'm producing ethene from the ethyl radical. And again, notice I'm also producing another alkane. So here is a typical problem that you might see. In this problem, I have 1,1-dimethyl cyclohexane. And when I heat this alkane up, one of the products I get is 1-methyl-1-cyclohexene. So the question is, well, how does this happen? And secondly, what is the other product that forms? Because as you see it in the top there, a radical reacts with another radical to produce an alkene and an alkane. So an alkane must have been produced as well. So if we look at this problem and try to figure out what's happening, we see that we lost a methyl group, right? And so what must have happened to solve this problem, we say, well, okay, a methyl group must have come off under homolytic cleavage and formed a methyl radical. And then that radical reacted to form, so a methyl radical, and then a methyl cyclohexyl radical. So that must be our solution, right? I heat this up, and notice, any one of these carbon-carbon bonds can undergo homolytic cleavage, but in this particular case, to get to our product, I have to dissociate homolytically at between that quaternary carbon and the methyl group. And the result is I get a tertiary radical plus the methyl radical. Now notice this tertiary radical has, so if we consider it our alpha carbon, it has three beta carbons to it, right? So a beta carbon here, the methyl group is a beta carbon, and of course 2 methylene carbons that are identical in nature. And so obviously one of those beta carbons, the methylene carbon, has 2 hydrogens coming off of it, and so I can abstract one of those hydrogens with the methyl radical. Upon abstraction, that second electron of that carbon-hydrogen bond goes to form my double bond. The result is methyl cyclohexene. The other product is going to be methane. The third reaction is called beta cleavage. So this is when I say radicals can degrade. So basically, a radical undergoes a cleavage, and this is an intramolecular type of interaction. So we'll look at the butyl radical. Here I'm drawing the butyl radical, and when talking about beta cleavage, it's important to understand that the nomenclature of the alpha carbon and beta carbon is a little bit different than what we just saw in the disproportionation. In the disproportionation, we can think of the radical as being the alpha carbon. For beta cleavage, the alpha carbon is actually a carbon that's attached to a radical. I don't make up the rules, I just enforce them. And so the beta carbon is still attached to an alpha carbon. What happens is the radical forms a double bond with one of the electrons between an alpha and beta carbon. And so you have one electron left over between that alpha and beta carbon. That electron goes to the beta carbon. And so the result is you're generating a new radical, so in this case an ethyl radical, and then you get an alkene. So we see that beta cleavage results in the production of another radical from a radical, so a smaller radical, and an alkene. As an example, we can look at this particular radical. So when we denote alpha and beta carbons, we see that there are 2 types of alpha carbons and 2 types of beta carbons, right? And so we have 2 pathways. In the first pathway, I'll slow that down just a little bit. So in the first pathway, we see that, again, the electrons going toward the alpha carbon. We're going to take that bond between the alpha carbon and the beta carbon, and one electron goes to form a double bond, and the other electron goes to the beta carbon. And so the result is, for that first pathway, is you get an ethyl radical, and then you get a terminal alkene, namely 1-hexene. Now, there's a second path that beta cleavage can undergo, And that second path is in the opposite direction, right, where I'm using now green arrows, so the electron can go to the other alpha carbon, and I get one electron from the alpha-beta bond going to form a double bond, and of course that second electron goes to the beta carbon. So in my second pathway, I form the propyl radical and one pentene. So notice I'm starting with a long chain alkyl radical. I end up with smaller chain alkenes. The last way that radicals can react is simply what we call dimerization. And this is when two radicals simply come together. So here I'm showing the butyl radical reacting with itself and forming a bond, right? And the result is, if I start with two butyl radicals, I end up with octane. So I end up with an alkane. Now, obviously, when you're looking at radicals and their reactions of radicals, you can have all different types of combinations. So we saw that butane, if we pyrolyze butane, we get methyl radicals, ethyl radicals, and propyl radicals. So all of those radicals can react in any combination, and you get alkanes from them. Now, one of the things that I would like to focus on throughout the semester is when a reaction is synthetically useful or not useful. And for synthetic purposes, pyrolysis of alkanes is not useful whatsoever because we get all these different products. However, industrially, it is a very important process. And we call this hydrocarbon cracking. And this is actually how we get our fuel today. So we take oil, which contains long chain alkanes, typically, a lot of hydrocarbons, so long hydrocarbons, and we heat them up, and in the process, so this pyrolysis occurs, and it starts to break down those long chain alkanes, and so we can get smaller alkanes that are 8 carbons or less, and those are useful to use as fuels. Now, alkenes will also undergo pyrolysis as well, and they behave fairly characteristically. So here I have 3-hexene, and if I heat 3-hexene up, I undergo homolytic cleavage, and it's always between an allylic carbon and a carbon adjacent to it. And the reason for this is because I produce allylic radicals. So here, in this particular example with 3-hexene, I'm producing an allylic radical, and I'm also producing a methyl radical. Now, the reason why this is important and very characteristic of alkenes is because allylic radicals are stabilized through resonance, right? So I can draw a resonance structure of this particular allylic radical, and that I'm donating an electron from the radical, and then I'm taking one of my pi electrons from my alkene, forming a new bond. The second electron goes to the other carbon, and the result is a new radical. Again, it's an allylic radical, but because of these resonance forms, that allylic system is stabilized through resonance. We see this in the bond dissociation energy. So if you recall, the bond dissociation energy of ethane is 376 kilojoules per mole. The bond dissociation of the allylic carbon-carbon bond is quite a bit lower at 300 kilojoules per mole. Now, I can look at a cyclic alkene, and I can do the same thing, right? When I Heat this up, this cyclic alkane, cyclohexene, has an allylic carbon. So I heat this up, and I can undergo bond cleavage to produce an allylic radical. Now, notice in this particular case, because it's cyclic, I produce a diradical, where one of the radicals is simply a methylene radical, but the other radical, the radical on the right, is an allylic radical. And that allylic radical, I can draw a resonance structure for, right? So I'm forming a new double bond, and then the remaining electron goes to the carbon on the top. And the result is a new allylic system, allylic radical. So it's still a diradical, but because of that, it's stabilized. Now, another method of preparing radicals is using molecules that contain very weak bonds. And examples of these are peroxides. So the structure of a peroxide looks like this, right? Where you have some alkyl group coming off of an oxygen connected to another oxygen. And the oxygen-oxygen bond is actually very weak. The bond dissociation energy of this is 159 kilojoules per mole. So almost half as strong as that of an allylic carbon-carbon bond. And so we can get dissociation to form these peroxide radicals. This is a very specific peroxide. It's called an acyl peroxide. And so you note we still have that oxygen-oxygen single bond. It's connected to a carbonyl, and we can get dissociation of that bond, just like I showed you in the first type of peroxide. And the result is these acyl peroxy radicals. So acyl peroxy radicals have a bond dissociation energy that's even lower than typical peroxides. And the reason for this is because I can take that radical and I can draw a resonance structure. And the resulting resonance structure is of equal energy, and so these two resonance structures really help to stabilize that radical, hence the lowering of the bond dissociation energy. And so we see that resonance stabilization is very important in all aspects of chemistry, but specifically for radical chemistry. Another type of compound that has weak bonds are called azo compounds. So an azo compound looks like this, right? It has some alkyl group coming off of a nitrogen that's double bonded to another nitrogen with another alkyl group coming off of it. Now the reason that azo compounds readily decompose is, if you think about this for a second, if I take and I cleave, so I'm not cleaving the nitrogen-nitrogen double bond. I'm actually forming alkyl radicals by homolytically cleaving a carbon-nitrogen bond. And I do this twice. So I'm forming a radical. The other electron goes into the pi system of nitrogen, and on the other side, the same process happens. So I'm actually forming now a nitrogen-nitrogen triple bond, which gives me nitrogen gas. The result is I also get these two alkyl radicals. And this process happens very easily. And one of our common reagents that we use is called AIBN. So AIBN stands for azo bis isobutyronitrile, and AIBN is commonly used as a reagent to initiate radical reactions. And if I look at the process of heating AIBN up, I get homolytic cleavage at both ends, to produce these cyanoisopropyl radicals and nitrogen. So I get two cyanoisopropyl radicals and nitrogen. Now the bond dissociation energy of this is 133 kilojoules per mole. So it's about the same as that of the acyl peroxides. And the reason for this has to do with, again, resonance, right? So if I take a look at the structure of this cyanoisopropyl cyanide radical, I can draw a resonance structure in which I'm forming a carbon-carbon bond from one of the carbon-nitrogen triple bonds, and the remaining electron goes to the nitrogen. And the result looks like this, right? So it's still a neutral species, but I'm getting stabilization through resonance. Now the ease in which we can produce radicals with these compounds makes them very good radical initiators. And so you're going to see from time to time these being used to initiate a radical reaction.